Okay, thanks for the introduction. This talk is about automating quantum Hoare logic with automata. And this is an ongoing project collaborating with Yoga and Yu-Fang from Academia Sinica in Taiwan. And today I will walk you through the motivation and the goal of this project and the overall structure of our framework. And we will go through some details about how we use automata to automate the reasoning of quantum Hoare logic, and finally the ongoing work and future directions. So there are two challenges using the original quantum Hoare logic in practice. First, the scalability. Assertions in quantum Hoare logic are Hermitian matrices, which grow exponentially with the number of qubits, creating a scalability issue. And the second challenge is the lack of automation, which means a lot of manual effort is required by the users. And overcoming both the scalability issue and the need for manual intervention is a key focus of our project. So let's take a look at what an ideal automated quantum Hoare logic verifier would be like. And a good verifier, suppose we have Hoare triple as our input. A good verifier can return a proof tree if the triple is valid. And we're definitely not there yet. And right now we are focusing on an applied fragment of quantum Hoare logic where the assertions are projectors, and which make them easier to handle. And also we require the user to provide loop invariants. We are working on extending to the full scope of quantum Hoare logic and some automated loop invariant generation. And essentially, our framework is a two-stage process. So in the first stage of our framework, we start by generating a skeleton proof tree based on the structure of the program. And at this stage, we decompose the original triple into multiple sub-triples, and we label them with the corresponding proof rules. And you'll notice that there are still some unknown intermediate assertions at this point. And we will solving all these assertions using the semantics. Using the semantics to the corresponding proof rule at the second stage. Now that we covered the overall structure, and then let's look at how we create the skeleton proof tree in the first stage. So there are 4 supported program statements in quantum Hoare logic. So the first one is the initialization and unitary transformation and multi-branch if-else and a while loop. So therefore, we can generate a skeleton proof tree in a recursive and standard way. So if you can apply sequential composition, then you apply it to the program and you split the program into many sub-statements. And for each statement, if it is initialization or unitary transformation, you just apply the corresponding proof rule. And if a statement is a composite control flow block, after you apply the corresponding proof rule, you also recursively apply the step 1 and step 2 to the body of that block. So here is an example. So the input triples program includes an initialization, 3 unitary transformation, and a while loop. And we decompose it using the sequential composition rule. And for the while loop, we further apply the corresponding proof rule for the loop body. Here is only the unitary transformation. And this gives us the skeleton proof tree. So now, how do we solve the unknown intermediate assertions? So first, you need to decide on how to encode the assertions. And second, you have to design the algorithm for applying proof rule backward. So you can derive the precondition from the post condition. Now let's talk about the assertion encoding first. In applied quantum Hoare logic, each assertion is a projector. And since a projector corresponds to a subspace in linear algebra, and a subspace is a span of a list of vectors, so we can use that set of vectors to represent the projector. So now, what is a good candidate for encoding a set of vectors? Here is my recommendation. We can use a tree automaton. So a tree automaton accepts a set of trees. And you can notice that the frontier of a completely binary tree is a vector. So this is the intuition of how we use tree automaton to encode a set of vectors. Now let me show you a concrete example. On the left-hand side is a level-synchronized tree automata, an LSTA that encodes the computational basis of a 3-qubit system. So each node is a state, and each edge is corresponds to a transition. And for example, starting from the state Q0, there are 2 outgoing transitions, which we label them with choice 0 and choice 1. And so what makes an LSTA different from a standard tree automata is that we also require that in a single run, for each level, every state should make the same choice. And what does that mean? And let's go through a run that an automata run that generates the vector kit 101. So we start from this state Q0, and for first level we chose the chose 1, and then we pick chose 0 and chose 1 once again. And this is this is a tree that corresponds to the kit 101. So we can make a comparison to verify this. So on the right-hand side is a decision diagram of kit 101. And you can see that the only non-zero branch is following these edges from the solid edges and solid edge and dashed and solid, and you reach this only non-zero amplitude. And we go back to the tree that we generate by our tree automaton. So you can also see that you follow the solid edge and the dash edge and the solid edge. And this is the only way you reach this 1 amplitude. And for the others, it will always be 0. And also, you can observe that for the first 3 levels. And for each level, there are 2 different choices. So this automaton can generate 8 different trees, and each one corresponds to a different non-zero position of a decision diagram. And so this is why this automata encode the computational basis of a 3-qubit systems. And now you can observe that the second level and the third level, they share an identical structure. So this suggests that if you add an additional qubit to a system, then for the corresponding automaton, you only need 2 additional states and 3 additional transitions to encode this set of vectors. So this means under certain cases, the size of the automaton will be linear to the number of qubits, even if we are encoding exponentially many vectors at the same time. and the size of the automata will still remain linear. Okay. So now we are left with the algorithm for proof rule applications. So we start with the easiest one, the unitary transformation. So if given a post condition A, the precondition for a unitary statement would be A sandwiched by U dagger and U, and this can be viewed as a change of basis. So therefore, the corresponding subspace is spanned by this set of vector, which is you simply multiply the original vector vi by a U dagger. So how do we do this in an automata level? So we use the Hadamard gate as example. So assume that you have an input vector as an left-hand side, and after applying Hadamard gate on the first qubit of the result should be look like this. And you can see that for the right hand side is actually an addition of the original subtree, and the right hand side is the subtraction of the original subtree. So this is how we can follow this idea and modify the automata to. Therefore, this is how we generate the new automata that corresponds to the set of vector that after applying the Hadamard gate. So you can see that the new we label the new state as the addition of the original subtree and the subtraction of the original subtree, and we propagate this level by level to the leaf, and we can calculate the corresponding amplitude by the symbol in the state in the name of a state. So for example here, the corresponding amplitude should be R1 R plus R0. So it's 1 plus 0 and so it's 1 and times the coefficient of Hadamard gate, which is 1 over square root of 2. So it's look like this. And don't worry about the size. There are many redundant structure here. So after we apply the minimization algorithm, the result automaton will look like this. So given an automata, this should be an automata for the computational basis of a 2 qubit system. And after we apply Hadamard gate on the first qubit, this will be the result. And also, we can generalize this idea to arbitrary linear operator. So we can use this idea to apply a linear operator to an automata, a single qubit linear operator. Yeah. So, and this would be really helpful for our implementation of initializations. So this is the result of the precondition of the for the initialization statement. So you map 0 to 0 and 0 to 1, these two projection. So the idea of this is we make 2 copies of this. So we make 2 copies of the original automata A, and the first one we multiply by the projector 0 to 0, and another one we multiply by the projector 0 by 0 and 0 to 1. And the union of these 2 sets will correspond to the target projector. And for the last part, it's common in Hoare logic that you have to have some order rule, so you can like strengthen the precondition and loosen the postcondition. And so in applied quantum Hoare logic, what you should check is the order of the 2 assertions. And here is projector. That means we have to check that if subspace A is contained in subspace B, or the projector, so that means projector A is less than projector B. So we have to check the subspace inclusion of two automata. And how do we do that? So to check that, you have to make sure that every vector ui is a linear combination of some vi from of the second set of vectors. So we can do that by constructing this new automaton. Basically, this is a new automaton that multiplied by a scalar variable, an a, and another by a scalar variable b. And we use the standard product construction in automata theory to construct the vector of any two linear combination of the set of vector v. And then we check that if for every vector in ui there is some vector here, and some vector here that is they are up to scale equivalent. That means that ui is a linear combination of the vector of the set of vector v. And this is only if this doesn't work, you can extend this idea, so you can have a 3 linear combination and 4 linear combination and so on. And for the ongoing work and future direction, so to extend applied quantum Hoare logic to quantum Hoare logic, the assertion, we have to find a way to encode the Hermitian matrices as assertion. So not only we have to encode a set of vector, we also have to encode a corresponding eigenvalue. And also for the order rule in applied quantum Hoare logic is simply a substrate inclusion check. But in quantum Hoare logic, then you have to check the Loewner partial order, which is you have to check the difference of two Hermitian metrics and make sure they are positively semi-definite. And which is really hard, even using like metric representation. And this is my talk, and thank you.
Yes, thank you very much, Fang-Yi. So, are there questions, please? Yes.
First, thank you for the talk. And I have a question. I have a question about the looping invariant problems.
Yes.
Okay, you know, it's a common knowledge that the generation of looping variant is a highly non-trivial things.
Yes.
In reading about quantum programs. Okay, especially for while loops. So my question is, how do you plan to incorporate the techniques of generating the looping invariant, which is commonly known that can be solved by reducing to a semi-definite programming problem. Okay, which relies on some mathematical or some other techniques. Yeah. So that's my question.
Okay. So thanks for the question. And also we have a paper last year. I think it's also PLDI. It's about how we summarize the body of a loop, and it turns out that you can use, for example, for Grover algorithm, you only need 2 additional variables, and you can summarize what happens inside the whole loop body. And so we kind of want to generalize this idea to the constraint of, or the loop invariant of a while loop. Yes.
Thanks for this nice talk. So I was wondering, when you are deriving from the post condition to the precondition, are you actually restricting the the pre and post condition in the form of tree automata, and you are deriving. Is it equivalent to deriving the weakest precondition in the subclass of states representable by the tree automata?
Yes, basically we are calculating the weakest precondition.
So when for some like conditional statement and while loop, how do you take the conjunctions of two projectors? Are you taking the span of?
So under our encoding, we simply means that the span of we only mean that this automata corresponds to the span of all the vectors that are accepted by it. So the subspace corresponds to the span of this vector.
Yeah. Okay. So when you take the disjunction of two projectors, you're actually taking the span of all states spanned by the states in the first projector and the states in the second projector, and you take the span of all these states, right?
Yes. Oh, I know what you mean.
Okay, I see. So here is a possible. I was wondering whether there is a problem that when you do this, like for example, for several steps, then the space spanned by these projectors will be very big, and since you are generating this automatically from the end of the program, maybe in the middle the condition is already very large space, yes. And in this case you cannot continue to prove that because it already spanned the whole space, right?
Yeah.
So do you have any way to avoid this problem?
I do notice this, but right now I'm thinking of how to because this is a compressed structure, so it's not easy to figure to pick one vector from it, so. So the answer is the solution is still I'm still working on it. Sorry.
Okay, thank you very much.